All right, practice exam. First one here, we're just going through a couple ways to activate alcohols using HCl. First step is going to be protonation. Going to make a good leaving group. It's just going to leave. Secondary carbocation. Hydride shift. Cl minus eventually comes in and reacts. Again, you kind of know where you're going. If you saw this, said, wait a second, the functional group was on this carbon, all of a sudden now it's over here. That should tell you rearrangements have to take place, or some other more reactions like that. Another way to activate alcohols is SOCl2. A little bit safer way than strong acid. Protonation. Turn this into, but at this point you have like a tetrahedral intermediate. Do an elimination, right? Because you have a good leaving group, chlorine. Take your pyridine and do a deprotonation. And at this point the Cl minus can come back in and do an SN2. And we have 3 arrows. Form a new pi bond between oxygen, sulfur. We kick out the chlorine. So you remake a Cl minus that can start doing these other reactions again, and we make SO2 gas, which helps drive the reaction forward as well. Also notice the inversion, of course. We've inverted stereochemistry because you have this SN2 step there. So this one, really wanted you to think about drawing free energy diagrams, and we could go through, perhaps I could have written this one better and added a step. But the biggest thing I want you to be able to think about, right, the big takeaways are, do you understand how there can be 2 intermediates? One could be higher energy than the other. The difference between a kinetic and thermodynamic product. A thermodynamic product is the more stable product. The kinetic product is the product that comes from the lowest activation energy hill. And what I probably should have done here, if you're reading this, right, first intermediate is higher energy than the starting material, second intermediate is higher than the first intermediate. The second step is the rate determining step, so it's the second step, so we have the highest hill there, activation energy. I should have said intermediate, from intermediate 1, the kinetic product is formed. And I should have said from intermediate 2, the thermodynamic product is formed. I should have said that, otherwise it's not clear that this happens. But there you go. Number 3, give the mechanisms for each step in the reactions below. Excess Grignard reacting with an ester. Going to add at least two Grignards, that's what you should automatically know. Going to go from an ester to a tertiary alcohol. Ester adds in, add tetrahedral intermediate, good leaving group, elimination. Now you have a ketone, another Grignard comes in, add tetrahedral intermediate, no good leaving groups. Now we do a protonation of all the minus charges. Make sure you keep these two things separate. So you should have overall minus charges until the last step when you do the protonation. Get your 2 products. Oxidation reactions, secondary alcohol to a ketone, you're oxidizing 1 CH bond. So you can use PCC or anything with chromium would work. Either one would be fine here. Primary alcohol to carboxylic acid, you need to use chromium because that chromium can oxidize 2 CH bonds. There's 2 CHs right here. If I just wanted to oxidize 1 CH bond and make an aldehyde, I'd use PCC in this case. So for this question, I'm looking for essentially this orbital overlap picture to explain why sodium borohydride and lithium hydride react differently. So I show a case here with an aldehyde where both sodium borohydride and lithium hydride both make primary alcohols. Then I show an ester with sodium borohydride and lithium hydride. Sodium borohydride, there's no reaction. Here there is. So esters have resonance. They can do resonance, and that makes this carbon of the carbonyl group less reactive, right? So if this is less reactive, you need a more reactive nucleophile because that carbon's an electrophile, delta plus. Sodium borohydride is not reactive enough, no reaction. Why is that? If you look at where boron and aluminum are at in the periodic table, boron's above aluminum, so aluminum is lower on the column. So it's a larger element, and the hydrogens therefore are not going to have as much orbital overlap. If you have less orbital overlap, that's a weaker bond, a more reactive bond. And that's why these react more readily, even though they all are H minus. So I'm looking for that picture, which we've talked a lot about. All right, 6, give the mechanisms for each reaction. So I'm showing the products. Have an epoxide with basic conditions, right? A negatively charged carbon from a Grignard, and an epoxide in acidic conditions. Different steps. So in basic conditions, the nucleophile reacts with the less substituted carbon, does like an SN2. Make sure we don't lose carbons. It makes like a pseudo tetrahedral intermediate, and you protonate, and that'd be like step 2. protonate, make the alcohol. Notice the trans products, the OH and the thing you added, are trans to each other. In acidic conditions, the first step you do is protonation, right? H plus is a really good electrophile. Protonate the epoxide. Solvent usually is the nucleophile in these cases. It goes for the more substituted carbon now, does an SN2, right? So different regional selectivity from basic conditions, acidic conditions. You do a deprotonation, you get your product again. It's still a trans addition, but the nucleophile went to the different side, different regional selectivity, the more substituted side. All right. Ester, or a lactone, is a cyclic ester. Lithium aluminum hydride. All you can do right here is draw H minus. Don't need to worry about anything else. Adds in, makes a tetrahedral intermediate. And of course, lithium aluminum hydride is reactive enough to react with something that's not as reactive as such as an ester. Adds in, kicks out, does an elimination. You've made an aldehyde, adds in again. Make a tetrahedral intermediate. No good leaving groups, so you protonate everything, and you get this linear alcohol now in the final step. Biggest things, don't mix these two steps. Wait until the very end to do protonations. I know you want to make that OH there, but wait till the very end to do all at once. Speaking of lithium aluminum hydride, it's the only one of our reducing agents that's reactive enough to react with carboxylic acids. We have to remember, right, we're so used to looking at the carbon of the carbonyl group that we forget this is a carboxylic acid. So it's going to react with the acid part first. And you're going to make H2 gas. You're going to make this O minus. And this is also the only time you worry about keeping the aluminum around. All the other ones you just draw H minus and go. For this one, you got to keep it around because the O minus reacts with the aluminum. So again, carboxylic acid, lithium aluminum hydride is a little more complicated mechanism. Reacts there. You do an intramolecular hydride reaction. So the hydride from the aluminum, right, which has a negative charge, adds in. You make a tetrahedral intermediate. This is a really good leaving group. Elimination. Get to an aldehyde, and then this essentially aluminum oxo species. But then you're kind of done with this. That's all the part that's different. And then you're just reacting an aldehyde, so you just pretend it's like H minus again. H minus adds in. You get a tetrahedral intermediate, no good leaving groups. You protonate, and you get your primary alcohol. Okay, another epoxide in acidic conditions. A little different this time. I want to draw it this way because there's one similar to this in our homework. So the first step still is protonation. So you protonate. Our solvent essentially is a nucleophile, so this is nitrogen, lone pair here. Which carbon is it going to react on? It's going to react on the more substituted carbon because we're in acidic conditions. So it's going to do an SN2, but notice, right, so this is a little different. You have to actually switch the wedges and hatches around, essentially. Because this is coming from the back and it's leaving, this nitrogen is going to have to be hatched, and the methyl that was hatched now becomes wedged. And then the last step is just a deprotonation, and you get your final product here. So it's the same type of reaction we've done before, but I wanted you to have practice with the wedges and hatches again to do those kind of inversions. All right, the last one here, pay attention. I told you it's an elimination reaction, so make sure you do an elimination, which means you're going to form a pi bond. So it's still an activation of alcohol. It's a simple E1. You're going to protonate. Leaving group's going to leave. It's very similar to actually the very first problem we did with HCl, except now there's no good nucleophile. And I told you it's an elimination. Things leaves, methyl shift, gets a tertiary carbocation. We do a deprotonation, do like an E1 to get our elimination product. And also water, we also lost here. I drew up here another similar type thing you'll see. Sometimes you'll see H2SO4. Again, when this gets deprotonated, we have a negative charge here. That's not very good nucleophile because it's stabilized by resonance. And that's why we'll be more likely to do elimination type reactions. But look for those hints, bolded and underlined, what the product might be when you're working through these things.